For audience who are here with us in Taipei on site, please get ready. And for audience who are with us online, we will start our session in 3 minutes. Thank you. All right, good morning, good afternoon, and good evening, ladies and gentlemen, on site and online. Welcome to the 2022 International Conference on Quantum Cryptography. I'm your MC today. My name is Rebecca. Hope you all ready for a full day conference here. And today, for our first tutorial session, we have our session chair on site here with us in Taipei. So, ladies and gentlemen, please welcome Dr. Bo Ying Yang. Welcome, Doctor. The floor is all yours.
Two things. Today's coffee breaks are 30 minutes because it's much more in person today. And I'm honored to be introducing an old friend, Professor Rainer Steinwandt of Alabama, the University of Alabama, I mean. And I think we'll welcome him to give the tutorial on post-quantum cryptography. Let's give him a hand.
Thank you very much. Let me try to share my screen if this works as intended. And if everything goes as planned, you should now be able to see my slides. First, I would like to thank the organizers very much for the opportunity for speaking at this conference. I think there is still a great need for more interaction between the quantum cryptography and the post-quantum cryptography community. So I really appreciate the opportunity to be here, at least virtually, at this conference. And I want to kind of make it clear from the beginning that my intention is in no way to make a case that post-quantum cryptography is the best since sliced bread and better than quantum cryptography, or the other way around. That's really not the point here. What I hope is that I can help in supporting the dialogue between these two research communities, and give those people who usually not so much dealing with the post-quantum crypto community a bit of a flavor and of an idea how this part of the cryptographic community approaches things and where things stand. The talk is on purpose not very technical, but I hope it will give a bit of an idea of the techniques and tools that play a role in this area. And so kind of the fundamental starting point in post-quantum crypto is that everything that the protocol participants do is classical. So we do not assume any quantum capabilities on the side of the protocol participants. We only assume classical communication channels. And the main motivation behind it is that we look for cryptographic building blocks and protocols that are fairly flexible in terms of requirements where they can be executed. They should be good to implement in software, possibly in hardware, or at least to be able to speed them up with hardware. So that the communication channels can be are assumed to be traditional networks, no ability to transmit quantum states. And quite a bit of the research effort goes into attacks at the implementation level, as this is simply a concern depending on where the cryptographic building block is used. Adversaries may have the ability to induce faults or to measure characteristics like execution time, power consumption, these kind of things. And with the idea that this is the goal, the compromise kind of one makes in this community, if you want, is one no longer aims at information theoretic security, kind of these very strong forms of security, but one is willing to make some assumptions. And I'll obviously say a little bit more about this throughout this talk. But it's kind of a key difference to some work, say more on the quantum cryptography side, in that here, basically from the beginning, we are not aiming at this extremely strong form of security guarantees, with the hope that we can obtain some efficiency gains in this way. And so what I want to start out with is give a bit of an idea. So if we are not working with information theoretic security, so how does one approach defining security in this line of research? And there are various approaches, but the common approach is one starts out with some kind of abstract model that captures kind of the functionality that we want and what our adversary is assumed to have in terms of fundamental capabilities. What can they access? Can they learn keys from old session? Can they decrypt things? Can they sign messages? Those kind of things are made explicit. Also, if we need some heuristics about certain primitives that we use, one tries to bake this into this model. The key point here is that whatever this model specifically will say, and it will look different potentially for a signature scheme than for a key exchange scheme, but the model does not kind of depend on any particular solution we have in mind. So the idea is to really characterize the security of the protocol task we have in hand, and then afterwards come with our protocol designs and see whether we can achieve it. And the idea is that then we hopefully find a way to argue, in the ideal case very formally, that any successful attack that we can come up with in this model violates something that we don't think to be plausible. Typical setting would be that there is some mathematical assumption which we are willing to make, and I named here one which some of you may have heard, some may have not. It's one of those used in the post-quantum community. This modular learning with errors problem. If we believe that this problem is hard, we try to show a successful adversary could actually solve this problem efficiently. Another approach that has been used, for instance, by NIST recently in their standardization effort in the post-quantum realm, they asked, can you try to argue that an attack against your scheme is at least as expensive as recovering a key from a modern block cipher in terms of certain resources? So one tries to play this kind of argument within the model, which, if successful, gives a fairly strong structural security statement, but one has to be aware it's in no way an absolute guarantee. Yeah, it's a model, so certain things will be outside the model. Commonly, anything on the implementation level is not covered in this initial step, but is nonetheless often a real threat. And sometimes we run into issues that we have proofs which are, say, very asymptotic in nature, and it's very hard to get any meaningful statements for concrete system parameters we need out of the theoretical analysis. That's kind of a bit always the struggle, is do we have tight reductions, those kind of things. And specifically on the side with quantum adversaries, where there are some design decisions to be made, is what kind of quantum capabilities do we give our adversary at hand? So while the users don't have quantum capabilities, it's post-quantum. Attackers are assumed to have some form of attack to quantum computing. And again, there are different approaches. For instance, if you have a cryptographic primitive like a hash function somewhere occurring, maybe it makes sense that you allow that an adversary can ask queries or evaluate this function in superposition. One can ask similar question with keyed primitives, like a block cipher with a key the adversary is not supposed to know. Do we still want to grant these kind of superposition access? There is a tendency on the cryptographic design side to make attackers as strong as we can. At the same time, we have to be somewhat mindful that the attack models don't make them too strong in the sense that we rule out any meaningful construction. So that's there are some design decisions here, what we accept and what we don't accept as valid attack models. And the one example I want to talk to a bit kind of how one model security, because I think it's a very important one, and it's somewhat close to say a quantum key distribution, which I think in this audience most people know more about than I do. So it's a key encapsulation mechanism. That's one of the primitives that's currently a standardization goal from NIST in the US. And fundamentally, the goal of this primitive is to be able to create a session key and send it to a party in a secure way. And so a key encapsulation mechanism, it's essentially consists of three algorithms. The generation part, it simply creates a public key and a secret key pair. And that's it. So it's the whole thing is very similar to public key encryption, just if you want a bit more restricted. So what the encapsulation does, which you can think kind of as an encryption, the encapsulation gets as input only a public key, and then it comes up with a random key. Think of an AES key, something like that. So it produces a random key and an encapsulation hereof, so kind of an encrypted version of the session key. And the idea is that one then uses the session key in moving forward, kind of to protect some payloads with some symmetric cipher. But the key encapsulation itself is only concerned with, all right, I produce a session key for you, I package it securely, I encapsulate it, and then we can send this package of the encapsulated session key to the owner of the secret key, and the owner of the matching secret key then can just undo the encapsulation, so can kind of recover the session key. That's what a key encapsulation does. Yeah, you have a public key that allows you to create a session key, and an encryption hereof, and the owner of the matching secret key can recover it. It's probably a fairly useful primitive, because combined with a symmetric encryption, you can do a secure message transmission. And so what is the standard notion of security for such a primitive? And so the one I describe here, not fully formalized, that's what we expect that such key encapsulation does. And the setup here is kind of you can think of it as a game. And the idea is you start out by fixing a class of adversaries that you consider efficient and that you worry about. That could be something like polynomial time adversaries, probabilistic polynomial time adversaries, polynomially bounded quantum algorithms. So kind of pick your favorite class that makes sense. So in the post-quantum setting, you probably want like polynomially bounded quantum algorithms there. And what we require is that there is no efficient algorithm that can win this game that I'm describing better than guessing. And the game is, if you want, fairly simple. So we create absolutely correctly a public key secret key pair. And then the adversary, kind of we're testing in this game, will ultimately get access to this public key. So it's kind of public key will go to the adversary. And then we create a random key. It's really just picked at random. And then we run the encapsulation algorithm to get a session key and a protected version of it, the encapsulation of it. And now two things can happen. We give the adversary this encapsulation and the key that is encapsulated, or we give the adversary this encapsulation and a random key that had nothing to do with what we did here. And the task of the adversary is to figure out what is the case. Did we give you the correct key or not? What this game tries to capture is, given the public information and the encrypted session key, you don't have the ability to find out anything about this key. That's captured here by this indistinguishability piece. And as a tool that we would give the adversary commonly is the idea, well, the adversary might get access to some old keys that for some reason get compromised, get lost. And to capture this, we give the adversary access to a little box that decapsulates anything that she wants, except the challenge. Of course, if the adversary could ask what's in the challenge, nothing would be secure. But with this one exception, the adversary can ask for decapsulation of anything she likes and gets this. And with all these tools, she should not be able to do significantly better than guessing what we did, which key she got here. To build these kind of tools, well, there are different approaches. What is fairly common is to say, well, that's a bit much what we're asking for, and one does it in steps. One comes up with a design that ignores the second piece here at all. It says, this decapsulation piece, ignore it for now. And that's what I mean by module. You start with something similar. And then one uses kind of tools from theoretical crypto, which says, okay, if you combine this with what you have, you will get the stronger security you're looking for. So you can kind of have this modular design, which is fairly handy. And if one goes into technicalities, things like if you, in your construction, somehow involve cryptographic hash functions, things can become a bit tricky what you can and cannot argue. But this is kind of, I would say, an important example of a security definition, even so not fully formalized, that we use to characterize primitives. There are similar games for signatures or for key exchange, and that's kind of the general flavor of how these things work. Of course, the key point that it all comes down to achieve the security, we have to assume something. As I said, we are not talking about information, it's already clear. We have to come from something. And unfortunately, the situation is a little bit inconvenient there, because Shaw took away kind of our favorite tools. Yeah, so anything which looks like factoring or finding D-locks in our favorite groups is not available in a post-quantum setting. In particular, this very popular tool, Diffie-Hellman assumption, which is very powerful to design efficient protocols, it's gone, because if D-log is not hard, Diffie-Hellman assumption is not hard. So we just don't have this anymore. And if we look kind of what's currently happening kind of in the literature and in the research community, there is not really the canonical path that I could say here, this is what we should do. There are various candidate platforms. I'll say a little bit something about this. But there is also still a lot of movement in the field. So it's, on the one hand, it's very good in that there's lots of research going on and research opportunities. If you want to see it on the more negative side, to say, well, given that we want to build things now that we want to use now, maybe we would prefer it a little bit less activity in the area. So one of the more conservative design approaches is to try to build something entirely on symmetric primitives. The motivation being, if we look what's out there in quantum cryptanalytic results, the results seem less devastating if we look at things like block ciphers, hash functions. Yes, there are results, but it's not as bad in terms of consequences as Shaw's algorithms. And so one of the designs for a signature scheme that is, say, fairly conservative there and builds entirely on symmetric primitives is Sphinx Plus. Very nice construction, and let's say certainly one of the mature proposals out there. But what is interesting, even there, say we are still at the point that we have to be very thorough with our analysis and be careful of how well we understand the analyses, because there's just a very recent result which went, say, very much into detail and said, well, if you look in your construction, you need a hash function. If you use this particular hash function, SHA-256 here, which has a very particular design principle, we can exploit how this particular hash function works and then put a question mark on some security margin. And so it's a problem that can be handled, but it shows kind of that even for very conservative designs, we still kind of have to be really thorough in our analysis, as it's really subtle details that can make a difference in the security estimates we have. And say Sphinx Plus is really not one of the aggressive ones, so it pays if you want a certain price for its conservative design with signature sizes. But even there is that we still have to be mindful in what we can trust there. The more, if you go more for efficiency pressure, you will find proposals that emphasize more, say, mathematical constructions. And there is, when you see it here, what I put down here, I would say is kind of the four main areas, four main mathematical platforms, areas that are explored in the community. There are other areas looked at, and it's good. And it's, if you want, a good time really to look at other candidates. But these are, apart from the symmetric constructions, I think this is fair to say, the most mature ones that get the moment the most attention. And there is clearly a need, I would say, in the community to get more mathematicians into the research, into the cryptanalytic research, because you see it kind of, if you look at the areas, it gets fairly specialized, yeah. And if you think back to, say, RSA, It's probably not a huge group of people out there who really know in detail how factoring algorithms work, but here it gets now a bit more spread out into a couple of areas, some fairly advanced tools. So I think we really would benefit from getting more experts in the community who have the specialized knowledge we need to have trust in these constructions. And let me just say a few words to each of these areas without getting technical. The very first one, I listed them in alphabetical order. So the very first one, which is listed there, I dare to say that's the most conservative approach. It relies on tools that are, say, well explored for decades. So the classic McAleese, that's the name of a modern proposal, but it really builds on a proposal that appeared in the cryptographic literature in the 70s. And what we have right now is pretty much unchanged. I mean, there are some minor tweaks, but it's pretty much a construction which we know from the 1970s. It's widely considered as secure. It has been looked at by many people. I think here one can say really people tried to break it and there wasn't dramatic progress. Main downside of this construction is the public key size, which is larger than in some of the other proposals, which for some applications might simply be an issue. And so the second area I mentioned there is isogenes of elliptic curves. It's kind of beautiful in terms of mathematics. Conceptually, it's attractive in that you would say, hey, elliptic curves just had a problem with Shor's algorithm. Here we could bring them back just with a different, from a different angle. Regrettably, that in recent weeks, if you follow the post-quantum discussions, there have been some fairly powerful insights that disqualified some of the designs in this line of research, which just shed some serious doubt on the security of those proposals. And so there was, so yeah, there's a problem in that area at the moment that prominent constructions just do not work as we hope for. It's beautiful mathematics, but from the practical security perspective, yeah, there's at the moment a step back. Lattices, kind of as an umbrella term here for several different proposals with various types of lattices, are very popular. This includes all these constructions using learning with errors, and in particular, and that's perhaps the most prominent example, is the recent selection that NIST had, Crystal Kyber, that fits in this framework of lattice problems. I will not go into technicality of those, but say that's an area, it will probably get more in, even more attention, given that now we have Crystal Kyber being recommended for the standardization. If you look, there's a lot of movement in the literature on lattice problems. And said if one can make further progress there, it would have immediate impact on important proposals. And kind of the fourth area there is, it's commonly known as multivariate cryptography, where the idea is you work with systems of polynomial equations over finite fields, where we don't have efficient algorithms to solve them, and use this as a starting point. There's also various proposals over the years. In particular, there were some very efficient signature schemes considered. Regrettably, here also more recently, a very promising proposal there were some insights that raise questions on parameter choices there. And so that's at the moment also kind of a little bit a step backward, if you want. And so depending on, I would say, where your personal favorites are at the moment, couple of people will say Megalese type schemes, error correcting codes, that's the way to go. That's very conservative, that's very secure. Other people favor certain lattice-based constructions. But there's clearly more need for research in this area. And it's really also a good time if somebody has new ideas for mathematical platforms. It's all not that stable yet, that there is no room for new ideas. I just want to give a very little idea of one of them, how they look like. So I give a very rough look at Megalese. The reason I pick it is that it's considered as one of the more conservative choices. If you look, for instance, at Germany's Federal Office for Information Security, they picked Megalese as one of the algorithms they consider as suitable when combined with a traditional scheme. Set in on NIST side, Megalese is right now not a recommended one, but it's one of those schemes. I think nobody would claim at the moment it's insecure. It's mostly a matter of efficiency considerations. At a high level, kind of the construction is fairly simple. So the public key is ultimately just a matrix with 0-1 entries. It's derived from a parity check matrix from a suitable error correcting code. That those details don't matter for this talk, but it ultimately comes down just to a 0-1 matrix. The encapsulation process I'm mentioned is really fairly simple. So what one has to do is one has to fix a vector which has a fixed weight, so a fixed number of 1 entries, the rest is 0. And then it's just a matrix vector multiplication combined with some hashing. So hashing is computationally not a big deal, so hash functions are fairly efficient. They are used here kind of to allow some confirmation checks in the decapsulation phase. But in essence, it's a matrix vector multiplication with a little bit of hashing. And you see kind of there, the key that is encapsulated is this hash value specified there. There's really not much going on. The decapsulation, when going into details, there's a bit something to explain, but also nothing really new. It uses a family of codes that is known for decades and just relies on an efficient decoder for this type of error correcting code. And that's pretty much all there is to it. So it's a fairly well understood scheme. It's not particularly complicated. To give an idea of the performance values kind of this scheme, I mean, if you look at the calculation, it's not expensive in terms of encapsulation. Decapsulation is not awful. The key size is the main criticism. This here, kind of the somewhat strange naming that's taken from the submission. It indicates kind of the length of the code that is used here, 3,488, and the 64 indicates the weight of the vectors we're using. And you see kind of the public key size are not convenient. Yeah. At the same time, depending on the platform you are, you say, I don't care about 260,000 bytes. My PCs, that's really not an issue. If you have another platform, you may care. It may depend on the application. So the secret key size is listed here. And this is kind of what's given here. That would be to encrypt the 256-bit key. So 32 bytes. I apologize, 128-bit key. 256, 8 times 32 is 256, sorry. So 256-bit key, kind of the standard security level you would want to start with in a post-quantum setting. So if you want to see it in all glory details, the link I gave here, that gives you to the full specification. And if you kind of want to see a position where this scheme is considered as suitable, that would be kind of an example of an agency going in that direction. So what I want to go next is a slightly more complex example, instead of looking only, say, transmitting a session key, but looking at kind of one level up, a group key exchange protocol. The idea being you have many users who want to communicate together with the same key. And I'll go kind of through one protocol and some decisions we made there. And this part that it's based on joint work with two colleagues listed there from a project we're just closing out. The goal was a protocol that we can run now. So we did the final demonstration with participants in 5 countries, just over standard internet. We wanted a decent provable security guarantee under some assumptions that nothing is absolute here. And the whole thing should be reasonably scalable, which means when you have more participants and not too hard to implement. We also had a project group that added some protections during the runtime of the protocol to the actual software, kind of with runtime verification to protect parts of the implementation. That's not a part that is really too relevant for the purposes here. So what is group key establishment? It naturally generalizes two-party key establishment. So you have maybe 2, but maybe 100 people or parties who want to establish a shared key. The network is the adversary. That's kind of the usual issue here. We want an authenticated key establishment. There are various choices one can make how authentication is feasible in the context. One choice one can make is you have a full public key infrastructure and you can use digital signature. Can be very meaningful. The road we will go here is that we do not have that, but that the users share a low entropy common secret. Think of a password that a human being can memorize. That gives some extra twists in the design needs of the protocol, as you may not endanger or must not endanger the password. But you have kind of these users, think of human users who have just this low entropy secret in common, no high entropy secret for authentication. And kind of a basic goal, like always for key establishment protocols, is forward secrecy. Whatever we do, if our passwords get lost, that cannot jeopardize session keys. Yeah, it's kind of very similar setup as for 2 parties, just here, more users. So I will kind of, before going in the protocol and in the security model, go kind of one step back. What do we really need right now from such a protocol? And so if we think of today, the existing quantum computers, they do not really seem to offer a speed up over classical attacks right now. Yeah. So I think most people would be surprised if this week somebody factors 2048-bit with a quantum computer. So an RSA modulus of that size. We have all these post-quantum candidates for signatures and chems, and we can kind of have debates, which is our favorite, which do we think the most secure. But it's still a fairly active area. And so one may think a bit more carefully, how exactly should we transition to this post-quantum solution? So there is the approach one can take, that would be the second bullet here. We go all in right now. We take the best post-quantum primitives we have. We rely on an assumption we believe in, maybe something based on lattices, maybe based on error correcting codes, maybe something else, and build a protocol on this. There are group key establishment protocols that go this line. I as I say, I list here some examples from the literature that they go down this line. You see, there have been proposals using Isogenes. There have been learning with error variant proposals. And that is an approach one can take and say this is the way to go. A different approach, that's the first bullet here, would say, we're not quite so sure yet. We want to see hybrid designs which use something which has worked for a couple of years. I still believe in our elliptic curve primitive or in this RSA-based construction, and you combine it with our favorite post-quantum solution, and you design the protocol in such a way that at least as long as one of them is fine, we are good. May come at a performance disadvantage potentially, as you kind of deal with two of primitives, but some people may feel better. And if you look kind of at the comments from the German Federal Office for Information Security I mentioned earlier, they mentioned that a hybrid design for using Megalese, use it as a hybrid with. And such hybrid designs have been explored, nothing wrong with that. If you're comfortable with the potential overhead there. A third item I want to kind of tackle here is what in the literature is sometimes referred to as a quantum future scenario that says, I design my protocol in such a way that if the adversary gets access to a quantum computer after I'm done with the execution, say in 10 minutes, that doesn't affect the security. But I need the assumption the adversary cannot access a quantum computer while the protocol is executed. So while I do my message exchanges here, I assume you will not be able to solve this dealer. The idea of going this line is maybe this allows you to use some more efficient constructions without really making you uncomfortable. Yes, I would say most people will be comfortable that the next 10 minutes, a classical primitive that has lasted the last years will still be fine. But this may allow us some efficiency gains. The full security model, I won't get into here. That gets kind of too technical for the purpose of such tutorial talk. But the basic idea is similar or is the same as I mentioned at the beginning of the talk. We set up our model where our adversary gets all kind of tools. And in this case, our adversary, they will get little oracles that control everything. So if we send messages over our network, the adversary is actually doing this. We call this a send oracle. So the adversary has full control over what is sent. Then we give the adversary the ability to reveal old keys that have been established. Because maybe that is of any good, or we just have to live with the fact that occasionally old session keys get lost. And multiple protocol executions can be run. All this is captured. The one kind of key component here is this, I call this here this QCOM, this quantum computing oracle. That kind of expresses in the model, and now you usually go into the basement and run your quantum computer. And the way the model is set up, you are not allowed to do this if you still keep running the protocol. You can run the protocol and afterwards do all computations you like. But once you have done this, you can no longer start the protocol again, because that was the assumption. Our protocol runs today and we keep it running until we really have a threat that we say, okay, quantum computing, it's here now. We no longer can use this protocol. That may be many years, depending on your view. Maybe that's only for 2 more minutes. But it's kind of the setting, yeah. This protocol is designed to run securely while quantum computing is not imminently available during the protocol execution. And then the security definition is framed in such a way that the adversary has to attack a session where a key has been established, where she doesn't know the key for trivial reason. It requires some work to formalize it. But this fresh essentially means you can't know the key for trivial reasons. There are a little bit of bumps or kind of caveats when formalizing it. As we have for authentication only a low entropy secret, we need a term here at the front which captures that the adversary might just guess the password. We can't prevent that. You guess the password correctly, yep, then you win. So that has to be captured somehow in the model. That's why we have perhaps a somewhat unexpected term here if you never work this password authenticated key exchange. Okay, so how does the protocol look like? So we have now our group of users. They have in common a password, and that's it. So the first round, what we do is each of our users will broadcast a Diffie-Hellman value. And it has a little bit of a twist. The Diffie-Hellman group uses as a generator the common password. There's some technicality to make sure the password lives in the right group, but that can be done with the right parameters. And then what you have here is a traditional piece of a Diffie-Hellman key exchange, just with a somewhat unusual base. In addition, all the users, except we need one distinguished user, an empty mu0, they publish a completely fresh public key of a key encapsulation mechanism, as I mentioned at the beginning of the talk. The security we need here is slightly weaker than what I mentioned there, but if you have one which meets the one we had at the beginning, that's certainly good enough. And so that's the first round. Yeah, everybody sends this Diffie-Hellman value, and everybody except one distinguished user sends a fresh public key of a post-quantum chem. It's not totally surprising that somewhere I need this post-quantum primitive because, well, we want a security against the quantum computer in some shape or form. So I need this somewhere. And that's kind of the spot where it comes in. Now round 2, which is already the last round. The idea now is that we use these chem public keys that we send around in the first round to distribute the actual session key to everybody. And we somehow have to deal with authentication because nothing in this first round was authenticated. So there are kind of two pieces. Let's look at this first piece. U0 has received from everybody a public key. I mean, everybody their own, but U0 has received from everybody a public key for a chem. And so what it do? Well, it just runs the encapsulation algorithm that gives you 0 for each user, a little key. And it will use this key to mask the intended session key in a package for that particular user. Yeah? So for user U5, it's K XOR K5. And K5 is obtained from the encapsulation key that user 5 has sent. And so the idea is if this encapsulation is sent to U5, U5 will be able to recover this little K5, and there is the common session key. How do we handle authentication? Because so far that was all no good. There was no authentication at all. The idea is that we use these Diffie-Hellman pieces that we send around in the first round to compute a lot of two-party keys. And we use those two-party keys to use a good old message authentication code to authenticate what we're sending around. This here is a technical term, which just means we need a secure message authentication code. Those things are out there. That's not not very hard to construct. And so it's kind of everybody kind of authenticates after the fact to everybody. This is what I've seen, this is what I've sent. And so everybody can then check that everything has been sent and received properly. And so everybody has to verify all these tags. It's not a super much computation, makes are fairly fast. And if everything is verified successfully, one takes this raw key here, and that's essentially the key you use for some reason of the model we're using. Keys also get a name. Yeah, that's the blue key, and that's the key. So the whole thing has only 2 rounds, and establishes a key among an arbitrary number of users, polynomially many. For those who want to go into technicality, that I'm not going into any proof details, we do need the post-quantum chem because our adversary eventually has quantum computer access. And so what you'll notice in the protocol, the session key is protected with the chem. The passwords go only in the authentication piece. And so once an adversary gets a quantum computer access, they can compute D-logs and they can figure out the passwords. That's bad, but it doesn't jeopardize any of our session keys, because at that time, quantum computing is here. It's time to move away from this protocol. All these extracting these MAC keys we need from the Diffie-Hellman keys, one can make this very simple by really just reading off certain bits if one chooses the groups carefully. I won't go into this, but that's something which can be handled without technical difficulty. What some people don't like, and again, one has different opinions on that, if we have one party, in our case we have that, U0, that determines the actual value of the session key. Some people say that's not good, you want it contributory, other people want that. Everybody should have an input on the value of the key. That's fairly easy to add to the protocol by just incorporating the Diffie-Hellman value sent around in the key derivation. So if you like that kind of requirement, that can be done. So how does this thing look like in terms of efficiency? So the protocol I talked about is on the top line. What you notice is we have only 2 rounds. That's what you kind of expect if you look at today's group key exchange literature and say forget post-quantum, you expect 2 round solutions. So we can do this here. But the trick we played was you don't have a quantum computer while we run the protocol, but you can have it eventually. There is quite some stuff to be sent around. Here with these MACs, there is quite a bit something to be communicated. The tools we use for authentication is fairly mild. Said we use a MAC, that's not hard to build. We use password, that's a fairly mild setting, password-based authentication. If you compare it to some other constructions like here, that's a design that started out with an adversary that's only passive and then applied a generic construction to make it actively secure using post-quantum signature. The price you pay with this approach here, you get some more, a bit higher route complexity. You see kind of, you also pay your price in descending. There's always this quadratic term, which is just there, which is a bit of a nuisance, but it's there. That builds on the assumption you have signatures, can be perfectly fine if you have them available. Down here, that's a true post-quantum solution, also working with signatures, post-quantum signatures, 3 rounds. So that's kind of the place we are in, yeah. So I would say we pay a bit in communication complexity, but we are not totally out of the ballpark. So. But it's 2 rounds and passwords, so not obviously greater in everything than the rest, but perhaps an interesting trade-off if this is something you really care about. now said we have run an actual experiment with it. And so for this project, the way it was done, there were some extra considerations. We wanted the ability, and did it in some place, to have cryptographic operations entirely on a hardware security module, just to have an extra level of security there. It comes at the cost that you have to push all your messages on this hardware security module, which may not be the fastest. We also, as put in some, or the colleagues in two other project countries, put in some runtime verification. And kind of, this gives you kind of an idea what came out of it in the end. So we used nothing exciting, standard elliptic curve, as is popular today, common hash function, off-the-shelf MAC. Key encapsulation was here chosen as something that was designed to be compatible with an AES 128 security level at that point. And we, for our calculations, we made decent use of hashing to get a little bit of a speed up when we used our hardware security module. What you see here is kind of, it worked quite nicely in the whole setting with the smaller group sizes we had. With this setting, it was done here. It got a little bit awkward once you get 40 beyond people. So there is room for improvement, but it's workable reasonably well, yeah. And so that's kind of, I would say, gives an idea of what is doable with fairly mild assumptions, yeah. We needed passwords, a MAC, and your favorite common, whatever you want to build it, and have a somewhat decent solution for establishing a group key. And so that was one slide too fast. So where do we stand? And so the situation right now for post-quantum is certainly more complicated than it was while we had RSA and our favorite decision development assumption. It's exciting with all the math that's going on, all the progress. There are some really solid candidates, yeah, things like Sphinx Plus, Megalese, and add your other favorite schemes there. There are some solid candidates if you need a signature, if you need a CAM, but it's not as nice as, say, with elliptic curves around, where you could just pretty much have a silver bullet what you could use. It is a bit more complex. There is a lot of opportunities, and I dare to say need for working on the mathematical side. Implementation security is nothing I've touched here on, but it's obviously a big deal, because with new platforms we have to revisit how do we protect against the different types of attacks, how do we do constant time computations, all those kind of things. That requires work. That one can think, as I kind of indicated in this last protocol, to perhaps have these intermediate construction, more with quantum future, integrate with what already works. And then kind of thinking forward, of course, what are meaningful integrations with quantum cryptographic tools. So when we have a couple of implementations there at different scales, how can we meaningfully interact, handle key management, all those kind of things. So I think it's exciting times. Yeah. And with this, I think I've pretty much reached the end of my time. So thank you very much for the opportunity, and appreciate your patience and for coming that early. Thank you very much.
Well, we thank Rainer for the great tutorial talk, which I hope lends a good alternate viewpoint and to those at the QCrypt. And I think we can now take some questions because we have plenty of time, and both on-site and online questions are of course welcome. And if you have if you are online and have a question, please enter that in the chat.
Or if there is any question, are there any questions on site first? We will check if we have any questions online right now.
Any on-site?
I think we have one question online. Let me pass the question to the professor, to Dr. Young.
So there is someone who is asking what is the advantage in using public key crypto to distribute asymmetric key and then use use that key to encrypt and decrypt the message. And this is in cryptography known as a hybrid type crypto system. I mean, as opposed to using PKC to directly encrypt and decrypt the message.
Yeah, it's a pragmatic consideration. So typically the interesting case is that the message or the payload you want to encrypt is fairly large. And the fast encryption schemes that we have available are symmetric ones in different flavors. And so for sheer efficiency reasons, what one is typically going for, you use this slower asymmetric tool to get a small key across and then go down to a high speed to a fast symmetric solution. So it's exactly as just said, yeah, it's a hybrid construction. You use the asymmetric part to get the key across and then the symmetric part for the bulk of the workload. In the context of key encapsulation, there's also this term of chem-dem paradigm. You have the key encapsulation mechanism, and afterwards the data encapsulation, which takes care of the bulk of the work. And so it's an efficiency consideration. There's a similar kind of issue there also, while looking, say, at dedicated key establishment protocols at all. Shouldn't we just use public key infrastructure and send the session keys around using the public keys? That's where forward secrecy comes in, because the idea is if you have one public key and you encrypt a lot of session keys under it, once that public key gets compromised, all your session keys are compromised. That's kind of where key establishment protocols have their perks.
Okay, so for those who are wondering online, so this is a two-part thing. One is for reasons of efficiency, and the other is really forward secrecy considerations, which I will now type into the chat too. And is there any other questions, either on site or online?
Let me check if there's any other questions online right now.
Guess we can wait another minute or two. 再1分钟没有，我们就Let's wait another minute to see if there's any other online questions. It takes some time to type.
Or anyone wants to raise your hands here on site in Taipei? Any questions or comments? No?
Okay, I think that's pretty much it. And let's thank Rainer again, and thank you very much for this excellent tutorial.
Thanks very much for having me. Appreciate it.
All right, thank you, Rainer. Thank you. And I'd like to thank our session chair, Dr. Yan, as well. Thank you for joining this session. And we will now take a little bit long break. We'd like to invite everyone to come back at 11 a.m. Taipei time.
Right. Right. And so and here is coffee break served near on the mezzanine on the third floor. And as usual, we have very nice coffee breaks. So please, everybody, enjoy.
All right, thank you. Thank you, Dr. Young, for the introduction of the coffee break. All right, so for the audience online, we will see you back at 11 a.m. Taipei time for our next session. Thank you.